Uh, Good afternoon, everyone. So we're not spend much time here. Time is short, so we'll skip directly to environmental stress cracking. What is environmental stress cracking? It's a well-known case of failure for plastic products, which is caused by the simultaneous action of two factors, a presence of a mechanical stress, and at the same time, the influence of some kind of active medium with an important thing to point out is that the medium does not have to be chemically aggressive towards the material. So it's not actually degrading the material somehow. However, it can strongly decrease the fracture resistance of said material, thus leading to premature failure of a given product. So three critical aspects leading to ESC are a certain degree of affinity which is required between the chemical agent and a polymer, the ability of the chemical agent to diffuse within the polymer, and also enough time for it to cause an effect. And this kind of phenomenon can affect really a huge variety of products because most polymeric materials are susceptible to some kind of these environments. The generally accepted mechanism to explain ESC is related to the typical way we conceive failures in polymers. Do you see also the pointer, Bamba? Well, I don't know, hope so. Anyway, you... okay, that's good. So I can use it to point out things. Typically, when we observe failure in polymeric materials, we observe the formation of a craze, which is the structure generating from an already present defect within the material. The craze starts to grow with the formation of some voids with this fibrillar structure in which the material is drawn from the bulk and the fibers are stretched unto the point in which they break. In presence of the active environment, the environment can diffuse within the craze and locally cause a plasticization of the macromolecules of the material. And this plasticization, which occurs because of the affinity between the agent and the material, basically makes it much easier for the fibers to deform and eventually break, thus reducing the mechanical strength of the material. The phenomenon has been studied extensively in the past 60 years, I'd say, or something like that. And the way it's described within the scientific community typically is related to a fractal mechanics approach, which is taken from the description of slow crack growth phenomena in general. However, before going into fractal mechanics, I like to discuss with you a couple of tests which are generally accepted as industrial standards to describe the phenomenon of ESC and to evaluate the resistance of materials to this kind of fracture. The first one is the bend strip method, which is generally used for rigid materials like amorphous polymer, like polystyrene seen before. And the idea here is that I take a tensile sample and put it on a template with an applied deformation, and then it's immersed within the medium. So you have the simultaneous presence of the mechanical stress due to bending and the environment, and then you test the sample and compare the strain of break with the same value of the strain of break, with the value of the strain of break that you obtain on a sample which has not been immersed. And of course, the reduction in the strain of break will tell you how much the material is sensitive to ESC. Another method is the generally accepted gold standard for polyethylene and polyolefins in general. It was developed in the 1950s by the Bell Labs. And the idea is, well, they were working on cable insulations. The idea is to cut the small samples, put a notch and a sample, then you bend it, put a stack of these samples in a vial containing the liquid, and then you record the time which is required to obtain failure in 50% of the specimens. There are a few issues with this kind of test. As you may notice, well, none of them is a proper fractal mechanics test. In a bend strip method, you don't have a notch. So the defect which originates fracture is not known a priori, depends on the defects left there by the production process. In a Bell telephone test, you have a notch, but the notch is put in a wrong way when you compare it with existing bending stresses, which would be parallel to the notch direction. So the notch will cause the initiation of fracture, but then the fracture will proceed driven by stresses which are not the bending stresses and would change direction. So in addition to that, the test is very geometry dependent, meaning that the bending stress that you achieve initially depends on the thickness of the samples and on the stiffness of the sample. There are some other unclear standard definitions, and in the end, this all leads to some kind of poor reproducibility of the results you get with this test. So this is why in the scientific community, many people rely to alternative methods to characterize ESCR, and fracture mechanics is one of those. And the approach is identical to the approach which is taken to consider in general stress cracking of polymers. In polymers, which are viscoelastic material, you assume there are two phases: initiation, which is the time required for the defect to become critical, and propagation, which is the time required for said defect to grow through the thickness of the product and cause failure. This is what you observe. You have a stress intensity factor, and at some point after blunting, it will become critical. Of course, the time for initiation will be lower if you apply higher load. But the characteristic property of the material is this relation between the toughness and the initiation time. Not a single Kc value, but rather a curve. And at the same time, once you have propagation, you establish a relationship between the applied K and the speed at which the crack will grow within the material. This is some example of data. Of course, the easiest loading case is a case in which I will apply a constant load, which is this situation, to this bending stress, which is notched. And here you can identify the pure creep region in which the deflection increases because of creep, and then the sudden increase you have when you have fracture initiation. So you typically obtain this kind of relationship, and it turns out that power loads can describe quite well the relationship between the existing parameters. And an important aspect of this approach is that you can not just rank the materials, but also make predictions on lifetimes of a given product once you know the initial defect size and the applied conditions in terms of K. Now well, of course, you can use this also to study the effect of the environment, provided you have some way of adding the environment in your testing setup. There are several options. For example, in Milan, we sometimes use flexible bags. This is something you can do, and it preserves the original setup in terms of tools and fixtures that you use. Of course, the bag is filled with a medium of interest, or you can build a tank, which hopefully fits your oven and testing machine, or you can build a custom rig. We have custom rigs. Imperial College also has one. Versailles. These are just some examples taken from people working in the ESIS TC4 on ESC, which I'm involved in. Okay, this is a strange configuration. I will tell more about that later on, because the first point that I like to address is that I mentioned that a defect of these industrial standards is that they're geometry dependent. So the first thing is to assess whether the fracture mechanics approach can instead be geometry independent, and also to check the influence of the loading history. And I will present you some results relating to a comparison between three different loading configurations: 4-point bending under creep, DCB, or 3-point bending under constant displacement rate, as you would do in a tensile experiment, or the buckled plate, which works in relaxation. And this particular work, two materials were selected, and it's interesting. It were two HIPS with rubber particles to toughen the polystyrene. One was a conventional grade, slightly better mechanical properties. The other one is a specifically tailored environmentally resistant grade. Here the environment is sunflower seed oil, whose properties are slightly worse in air, but it performs better in oil. And here there are different ways of measuring the parameters you need. with our setup with the creep ones, we use the compliance method to characterize the crack length. This is something you can do even when you cannot see the sample. And you know that the compliance depends on the creep compliance of the material and the function of the notch length. So by recording the compliance, you can know what the crack length is at any time, detect initiation, and then measure propagation. When you can see the sample, as for example in this case, for the constant displacement rate test, you can use an optical method to record the crack advancement, so you can get all the information you need. And with a buckle plate configuration, this is a bit more peculiar. Here you apply a constant this bending to the plate, and you start with mode 3 conditions in which the crack driving force, which is given by this energy release rate term, only depends on the material models and the geometry. And it's constant in the first stages of the test, in which you expect also a constant crack propagation rate. It's hard to detect initiation here, but you can get propagation data. If you look at the results here, these are some example of these results. You can check some interesting facts. This is the typical outcome of a fractal mechanics experiment to study ESC. And you see that the blue curve is indeed higher than the red ones because the non-ESC resistant material performs better in air. But as soon as you introduce the environment, you see that indeed things change and the red ones eventually becomes better. Here, other things you can see, all the data fall together irrespective of the configuration. So indeed, these results look geometry independent. And also, you see that the effect of the environment is huge because at a given K rate, K value, you can have orders of magnitude in initiation time. Typical values, of course, are low here because you don't expect failure of products in a few hours. And you can identify a critical interaction time. Well, if the load is too high, failure will occur before the medium has time to diffuse within the polymer and play a role. If you wait more, typically with lower K, then the effect of the environment will be more and more important. In propagation, you see quite similar results with all the data. Of course, in propagation, you have more data points, but the trend is the same, the blue over the red, then the huge effect of the environment after a critical crack propagation speed, so meaning low K values, and you have this inversion. So you expect the material which is ESC resistant to actually perform better for low value of K, which are typical in the applications. A second, so we can use fractal mechanics to characterize this kind of data. In the next few slides, I will present some aspects of the ESC testing which are non-obvious. In particular, so far we follow the linear elastic fractal mechanics approach, which seems to work quite well with polystyrene. What about different materials like polyethylene, which is used to make bleach bottles? The problem here is storage, and when the bottoms the bottles at the bottom suffer from the load of the stacks of the one stacked above. Here, the problem is not bleach itself. The material is chosen to be resistant, but commercial bleach includes surfactants, which are a well-known ESC agent for polyethylene. Here, the effects that we will consider will be nonlinearity and temperature. Well, if you look at the data, the situation is similar to what we've seen before, with this relationship between the applied load and initiation time, the effect of the environment. Ideally, instead of using K as a representative parameter for describing fracture process, you could use G, which is an alternative approach. For example, Bamber and his co-workers at Imperial done that, and it works nicely. They're in linear elastic fractal mechanics, the two are completely equivalent. And indeed, the trends are the same. You get the same characteristic times, and you get these values for the critical interaction parameters. However, the relationship which goes between the two materials, well, uses a modulus as a way to get from G to K and vice versa. Of course, being a viscoelastic material, like many polymers, these models will be time dependent. You could say, okay, well, no worries, I will perform a relaxation experiment. You can do that and get a modulus as a function of time. The problem is that with many materials, these models will be strongly strain dependent because of the material nonlinearity. so that you, for example, can see that even in a range in which you only are considering a few percent of strain, you have an order of magnitude variation on the models. So can we still try to make a comparison between G and K data? Short answer is yes, provided we take strain correctly into account. To demonstrate that, I have the slide in which we basically took G data and K data and used them to determine an effective modulus which is based on this equation. And not only all the data points fall on a single curve, but what you can also check is that the curve of modulus versus time that you obtain is related to the value of the strain that you would expect for a sample bent like the fracture samples you are testing. So the answer is yes, it works. You can use G or K as you wish, but be careful because these are viscoelastic materials, so it is important in your analysis to consider the correct value of strain and time. Another aspect which is interesting is the effect of temperature. Temperature is used frequently in environmental stress cracking testing because tests can take quite a long time. So you typically use a temperature to accelerate the tests, which works fine as long as the increase in temperature does not change the activity of the medium, of course. Up to 60 degrees, well, typically things are not severely affected. In this data, I'd like to show some results on the polyethylene we've seen before, taken at different temperatures. These are the previous data. If you look at 50 degrees, you see a very similar trend, but as you see, you will see that as you increase the temperature, the curves rise a little bit, as you would expect, because things slow down, so you will need a higher K to get fracture in the same amount of time. And here it's the curve at 23 degrees in which you also see the brittle, the ductile failure region. Actually, it turns out that you can try to superimpose all the data together by applying time-temperature superposition, which is a well-known reduction scheme which is used to treat mechanical properties of polymers. And basically, it means that you can shift curves at different temperatures to obtain a single master curve. And you can see that the shift factor, which is the amount you need to perform this translation, indeed turns out nicely for all the conditions. This is an important result because it says a few things about ESC. It means that, at least in this case, since the shift factor is the same in air and the environment, the acceleration factor is only due to the material viscoelasticity and not to a change in the ESC process itself. And this is interesting because it means that you are free to change the temperature as you wish to accelerate testing. But not only that, you can take data from the test you perform at high temperature to rank the different materials, for example, at 60 degrees, and use those data to make predictions about the expected lifetime of products, which, for example, work at 23 degrees or not much different, like the bottles which are stored somewhere before being put to the shelves. Okay, now I will, well, run a bit fast probably, but I think I had some time to talk about, to point out some conclusions. I hope that with this short lecture, I convince you that environmental stress cracking can be a very important phenomenon because we've seen that it can really decrease the expected lifetime of some products by orders of magnitude, and so it's very important to find out whether the polymeric material which is chosen in a given application can be affected by the environment. Of course, it doesn't mean if the environment is in contact and while the material is not loaded, because you have to keep in mind that only when you have the simultaneous presence of the environment and the mechanical loading can ESC occur. So you can immerse, for example, in a given medium for 2 years, but if the medium goes away before you apply some mechanical load, nothing bad happens to the material. However, if you have the simultaneous presence, then you have to be very careful. There are some standards to characterize the resistance to this phenomenon. However, they're a bit lacking in terms of the accuracy and their sensitivity. And also they cannot be used to make predictions. So you can tell, okay, material A is probably better than material B, but I have no clue as to how long a product may last in those conditions. While fractal mechanics, even the most simple linear elastic fractal mechanics, can provide a good answer to this. Because it can provide data which is independent of the geometry and of the testing configuration. And with some attention, you can also include some nonlinearity effect, adopting a sort of pseudo-elastic approach by considering the proper values of the strain and time for the modulus. You can also consider the effect of temperature, which can use at freedom to accelerate testing, whether it's needed. Of course, this is all valid as long as you are in plane strain conditions, which are the typical conditions you use for testing. However, on some materials, including, for example, polyethylene, when you have plane stress conditions, such on thin products, then probably the amount of plastic deformation you develop will be much higher. And so for stress cracking, as for environmental stress cracking, you will need to rely on something else like elastoplastic fractal mechanics, which of course is more complicated, but in those cases can give you more accurate results. And I think my time is probably over. So I will thank you for your attention, and I will